Good morning and welcome to Tech 293 for Thursday, March 4th. In this video, we're going to talk about compression testing and also the instructions for Lab 6. But let's start by talking about the schedule. So you can see in the schedule that we have Lab 5 due. The Lab 5 lab report is due on March 11th. So that's actually the next class session because we are not going to have any class or videos on March 9th. That's next Tuesday because that is the equivalent of spring break. So we're not calling it spring break this year. We're calling it a personal well-being day. But that's what it means. We're not going to have anything, any class or anything on March 9th. So Lab 5 lab report is due on March 11th. That's next Thursday. And then we also have Quiz 4 coming up. Quiz 4 is going to be due on March 7th. That's this coming Sunday by 11:55 p.m. And I will tell you that there's nothing on Quiz 4 about anything that we talk about today. All right, so everything on Quiz 4 has to do with material that we have covered before today. So if you're caught up on the videos and labs, you're all ready to do Quiz 4. Quiz 4 is mostly about ferrous metals that we've talked about in the past couple of classes, as well as tensile testing, and maybe a couple of calculation problems related to tensile testing. All right, so the schedule says today we're going to talk about compression testing, and we're going to discuss Lab 6. That's the lab on compression testing. Both of those will be really quick because there are actually a lot of similarities between compression testing and tensile testing. So there's not that much to talk about with regards to compression testing and the Lab 6, which is compression testing. So I think what I'm going to do, I think I'm going to make two videos today, and I'm going to combine compression testing, like the conceptual part, and our instructions for Lab 6 into this video that you're watching right now. And I think I'll make a second video and post it today about non-ferrous metals. So on the schedule, that is on March 11th, but I think I'm going to post it today because that way on March 11th, all we'll have to do is Lab 6. So you'll come into the lab on March 11th to do Lab 6 in your lab groups. And that's all that we'll do on that day. So I'm going to make two videos today. This first video about compression testing and Lab 6. And the second video will be about non-ferrous metals. All right, so that is about it for the schedule. So we're going to talk in more detail in this video about compression testing and then the instructions for Lab 6. And the nice thing about compression testing is that it is really similar to tensile testing. We're going to do it on the Instron machine. It's just that instead of pulling specimens apart, we're going to squish them together. We're going to compress the parts together. And it's very similar. We're going to have a lot of the same regions on the stress-strain curve. We're still going to calculate stress. It's still force divided by area. It's just that the force now is trying to squish them together instead of trying to pull it apart. But we still have compressive stress. We still have strain, so that's still going to be the change in length divided by the original length. We're still going to have a linear elastic region where we have elastic deformation. And then there will be a nonlinear plastic region after we exceed the yield stress of the part. So most of the differences that we'll talk about today have to do with that plastic deformation region. And we'll talk about those in just a second. You know, one of the only differences I can really think of off the top of my head about between tensile testing and compression testing in terms of your calculations has to do with the gauge length. So remember in the previous labs, to calculate the strain, you take the change in length divided by the gauge length, where that was that like the skinny length of the test specimen. Well, in these specimens for Lab 6, here's some examples of half of the specimens that we're going to do in Lab 6. In my right hand, I have some acrylic and some polycarbonate, and in my left hand, I have some aluminum, and I've also got some other kinds of woods and some steel that we're going to compress as well in Lab 6. But as you can see, these don't have a skinny section. So the original length is just the total height of the specimen. And I'll tell you what it is later. Actually, I'll go ahead and tell you what it is right now. The diameter of these specimens, for all of them, is 1/2 inch in diameter. So that can tell you the original cross-sectional area. And then the original length, so you'll need that to calculate the strain. The original length is 1 inch. So for all these specimens, the diameter is 1/2 inch and the initial length is 1 inch. And I didn't just decide that. That's based on the dimensions that are given in the official ASTM test procedure. So it generally calls out some standard specimen dimensions for all these different kinds of parts, tensile testing and compression testing and V-notch testing that we'll do later. And these are all based off of the ASTM procedures. So that's probably enough introduction. So I'm going to go ahead and share my slides and we'll talk a little bit more about compression testing. Okay, compression testing, let's get started. All right, like I said, it's not very different from tensile testing. We've still got stress, and you'll calculate it the exact same way, force divided by cross-sectional area. You still got strain, it's still calculated as change in length divided by original length. What you're gonna see in the stress-strain curves is we still have a linear elastic region, and we still have a yield stress. So the elastic region is gonna look pretty similar to a tensile test. It changes after that. After you get into the plastic deformation region, it looks different. But up until the yield stress, it looks pretty similar. In the elastic deformation region, that is the linear elastic region up until we get to the yield stress, what's happening is kind of the exact opposite of what happens in a tensile test. In a tensile test, you're stretching the lattice apart. So the inter-element spacing in the lattice is actually getting very slightly smaller as you stretch it in the elastic region. And you don't start getting parts of the lattice structure to slide past other parts of the lattice structure until you get into plastic deformation, because that's plastic deformation. But in the elastic deformation region for compression testing, it's just the exact opposite. The inter-element spacing in the lattice structure just gets compressed. It just gets squeezed closer together slightly. So it reduces the inter-element spacing in the lattice slightly. And then just like before, if you compress something but you remain in the elastic region and then you release the test, then it's going to spring back just like a spring. So this is, in a sense, just kind of like a spring that you're compressing instead of a spring that you're extending. All right, when we get to plastic deformation, then things are a little bit different. So this is after the yield stress in your compressive stress-strain curve. And basically, materials will behave in one of two ways once they get to the plastic deformation region in compressive testing. And what they do in plastic deformation kind of depends on the properties of the material. It depends specifically on how ductile or how brittle the material is. If you have a ductile material, then what's going to happen is it's going to start squishing it, and you're going to get what's called barreling. And barreling looks kind of like this, where if you squeeze it, then the material's got to go somewhere, right? So it starts bulging out on the sides. So you could also think of barreling as bulging, but bulging is not the technical term. The technical term is actually barreling. Why? Because I suppose this kind of looks like a barrel, I guess. So that's what we call it. We call it barreling for ductile materials, which basically means if you kept on squishing this and squishing it, or compressing it, then eventually you'd end up with, something that looks kind of like a pancake, a pancake with bulging sides out on all sides. So that's barreling. That's what you get for ductile materials. If it's a brittle material, like it looks like some kind of a ceramic or probably concrete here, and wood tends to be a pretty brittle material also, what you get is not barreling. You don't get it to push out on the sides. It doesn't bulge out on the sides. What you get is something called shear fracture. And basically that just means that it fails in a brittle manner. It fractures, it cracks, it starts cracking, and the cracks propagate through the material, and it fails in this manner through fracture. All right, so that's mainly the two ways that materials will fail in compressive testing, either via barreling or via shear fracture. Here's an example of what a stress strain curve will look like for a compressive test. Notice we've still got stress on the vertical axis. It's still measured in PSI. We've still got strain on the horizontal axis. It's still measured in inches per inch. And we've still got a fairly similar looking curve here. Notice there's quite a lot of toe compensation here. Hopefully you won't see that in your tests on Lab 6. But if you do, you know, so be it. What you need to do is just measure the slope in the linear elastic region. So as you're picking 2 points to calculate the slope between, if you've got toe compensation like this, don't pick the origin as one of your points, because then you'd be calculating the slope of a line that goes from the origin up to, you know, up here, wherever your second point is. So if you don't have toe compensation, then it's fine to pick your origin as one of the points. But if you do have toe compensation like this, then make sure that you pick 2 points within the linear region of the curve. Okay, we've still got a yield stress. That's where it transitions from the linear region to the plastic deformation region, which is a curved region. And we still have the definition of the elastic modulus. It's still the same definition, but we need to specify when we're talking about it that it's the compressive modulus, or the modulus in compression. So it's still the slope, rise over run, change in stress divided by change in strain. And so if these are my 2 points, here and here, and I'm going to calculate the slope between them, I take the difference in stress, because that's the rise of this triangle right here. The rise is the difference in stress, 10,000 psi minus 2,000 psi, and the difference in strain is the run of this triangle, and that is 0.012 inches per inch minus 0.005 inches per inch. Do that calculation and you find that the compressive modulus is 1.143 million psi. All right, here's what a stress strain curve looks like for a material that's going to barrel. What you're going to see is that if you are testing a material that's going to barrel, what's going to happen is the stress is going to come up linearly to the yield stress, and then it's going to curve over into the plastic region, and then it's going to increase, and it's basically not going to stop increasing, because what's actually happening is this cross-sectional area is increasing and increasing and increasing. This is kind of like our discussion between engineering stress and true stress, right? So we are doing engineering stress, and we're not accounting for that increase in cross-sectional area. We're always just using the initial cross-sectional area. But what's actually happening is, as we do this test with barreling, the cross-sectional area is increasing and increasing. And so what's going to happen is that our stress is going to continue to increase. I mean, in theory, it's going to increase indefinitely. In practice, you know, something's going to give. But in theory, you'd have a curve that looks like this. You got your linear elastic region, you got your yield stress right here, and then this is the plastic deformation region. And if you keep on pressing it, the stress is going to go up and up and up and up and up. And because of this, we don't usually talk about the ultimate compressive strength. That's not a thing. The ultimate compressive strength is not usually measured as a relevant parameter because of this. Because if you keep on squishing it, the stress is going to keep on going up and up and up. So we don't have a peak in the curve necessarily like we did when we were doing tensile testing. All right, so when you do these plots in Lab 6, I'm not going to ask you to label the ultimate compressive strength. All right, I'm going to ask you to label the yield strength. but I'm not going to ask you to measure the ultimate compressive strength. All right, so when you're doing the calculations and analysis for Lab 6, it's very similar to what you did for Labs 4 and 5. You're going to get a CSV file, and you can open that in Excel. You're going to convert the force column to stress by taking the force divided by the cross-sectional area. You're then going to convert the deformation or extension, which is actually compression, of the parts. You're going to convert that into strain by taking the change in length divided by the original length of the part. And you're also going to calculate the elastic modulus in compression, and you're going to identify the compressive yield stress for your parts, your specimens in Lab 6. All right, that's about it for our discussion of compressive testing. As you can see, it's really very similar to tensile testing, so there's not a lot of things that we need to talk about. Probably the most important things were the ideas of barreling and shear fracture, and the ideas that ductile materials will barrel and brittle materials will fail via shear fracture. All right, so since that was pretty short, I'm going to go ahead and go right into the discussion of Lab 6. So let's go ahead and talk about what we're going to do for Lab 6. All right, Lab 6 starts on page 59 of your lab manual. And what we're going to do in this lab, we're going to use the Instron machine, just like we did in Labs 4 and 5. But we're going to use a special compression testing fixture, which you probably haven't noticed, but it's been in the lab when you were doing the labs previously. And this is kind of analogous, I guess, to the grips for the tensile testing, which we put the specimen in and then use to pull the specimen apart. But what we're going to do is use this compression testing fixture, and it's got a safety shield. So what you're going to do is you're going to open up the safety shield and then put the specimen inside of the fixture and then close the safety shield. And what that does is put a layer of protection in between the specimen and you. Because these things, you know, when you're compression testing something, it can fail kind of catastrophically. It can. So compression testing could be considered a little bit more dangerous. Don't get me wrong, I'm not overly concerned, but it can be a little bit more dangerous than tensile testing, just because if something fails via shear fracture, it can sort of blow itself apart. It can kind of explode. So it's a good idea to use this compressive testing fixture. That way we have a protective shield in between the specimen and ourselves. The specimens that we're going to test, we're going to use two different kinds of wood. We're going to use two different kinds of plastic. That's what I've got here. This is the polycarbonate. It has black dye in it. And this is the acrylic. And we're going to use two different kinds of metal. We're going to try out the aluminum 6061 and some 1018 steel. They're each going to be the same size. They're all 1/2 inch in diameter, and they're 1 inch in height. And as I mentioned before, I didn't pick those dimensions at random. Those are the dimensions that are suggested by the ASTM testing instruction document. All right, the machine preparation, this will be set up already for you when you come into the lab. So what you need to do basically is insert the specimen. So you got to raise up the plate by pushing that up button on the Instron machine, and then you need to slide open the testing fixture. That's that protective plastic plate. Slide open the protective shields and then insert the specimen and then close the protective shields, and then you're going to press the down arrow on the Instron machine. It's kind of hard to describe, but you'll see this when we get in there to test. You're going to press the down arrow until the Instron machine is about 1/8 of an inch above the test fixture. All right, and I know that's kind of hard to visualize right now, but you'll see that when we get into the machine, into the lab. Okay. All right, then you go to the PC, running the software, press the test button, and you're going to click on the testing procedure called TEC 293 compression testing. Just like before, enter a sample name. Make sure it is specific so that you know which file is yours. Then click Next. Then once again, this is really important. You got to zero out the machine. So make sure you zero the load by clicking Balance Load and zero the extension by clicking Zero the extension. That zeroes out everything on the machine so that you're starting from zero, from a fresh slate when you start the test. Then you press Start, and you're going to see real-time updates on the screen, just like you have before. And this test is going to stop automatically on any of these test conditions. So when it reaches a strain of 1/2 inch per inch, in other words, we have our 1-inch samples, so when they have been compressed by 1/2 inch, then it's going to stop. Or if it reaches a force of 20,000 pounds force. And I told you before the capacity of the machine is 22,000 pounds force, but I built in a little bit of safety margin there, so when it reaches 20,000 pounds force, it's going to stop. So either one of these, when they are reached, whichever is reached first, that's what's going to stop the test. And then you remove the test specimen from the fixture, click Finish. That's going to save the file, and then it's going to ask you, do you want to repeat the test with another sample using the same test procedure? And we're going to use the same test procedure for all of these. And so if you have more specimens, then click Yes. If not, then click No. And if you do, then you repeat all the steps from step 5. If not, then you're done. Okay, then when we get into the results in the analysis section, I want you to calculate the engineering stress. Remember, that just means use the original cross-sectional area. And the compressive strain, that's just change in length divided by original length at each data point. That's in the Excel document. And you don't need to show all of the raw data in your report. That's just kind of a waste of space. So do all of that in your Excel document, but you don't need to show me all of your data. But I want you to construct a stress-strain diagram for each of the specimens. Like before, label the axes with units. The horizontal axis should be the strain. The vertical axis should be the stress. Make sure you use engineering stress. I want you to label the point where the yield strength is reached. Notice that there isn't anything here about labeling where the ultimate compressive strength is reached, and there isn't anything about a failure stress, because some of these, if they barrel, then they're not necessarily going to fail per se. So there is only the yield stress. That's the only point I want you to label in these. And then, like always, label each diagram with a figure number and then a brief description after that. Okay, for each material, I want you to calculate the compressive modulus, E, and show those results in a table. I also want you to make a table showing the compressive yield stress for each of the materials. And then for the discussion questions, I want you to write a good paragraph or two comparing and contrasting the properties of each of the materials. And most importantly, make sure you justify your answers and explain how you got that answer. How do you know? What about the plot or the table tells you this answer? So I want you to tell me and explain which material had the highest compressive modulus, which had the lowest, which had the highest compressive yield strength, and which had the lowest, and which materials barreled, and which materials fractured. Then a couple of applications questions here. If you were designing a support structure underneath a bridge, which of the materials from this lab would you choose? Explain why. And then if you were designing a support pedestal, that's like this part right here. If you're designing this part for a piece of mechanical equipment and you want this foot to dampen the vibration from the equipment, then which of the materials would you choose from this lab? And lastly, if you're designing a 2-story wooden deck, and this needs to be a piece of wood, it's a wooden support structure, a wooden support column, then which of the wooden pieces, which of the wooden specimens from this lab would you choose? And explain your answer. All right, so that wraps up our discussion of compression testing and our review of Lab 6. Make sure you look at the schedule for when you should come in to do Lab 6 in person, and I will see you in the lab.